In programming, object is a heavily overused term. If we're talking about C++ environment, its design is such that it's a general purpose programming language that you can write applications in it, you can write device drivers in it, or other components of operating systems. You can write really resource demanding and fast and efficient applications such as video games. So its speed and efficiency comes from the idea that C++ layer of its function, its implementation, is very close to the level of hardware, right? So the hardware is the fastest part of the computer. Software does things in loops and repetitions and so forth, requiring computations, so it kind of slows down the computer. But at the same time, the C++ is designed to give you something that runs directly, very efficiently on a specific hardware. So in general, going back to an idea of an object, in C++, the meaning of object is a blob of data which is considered to be a single item, and that's occupying specific memory, right? So something in memory is the idea of an object. A variable such as count or str over here simply names that object. Declaration is a statement. It means that declaration is not something formal. Declaration requires computational resources. So like when you're doing multiplication or division or addition or subtraction, of course it requires computational resources. Creation of the variable and its initialization likewise is consuming some CPU cycles, and so it's an executable statement. So generally, just technically speaking, this statement is not something that is consumed at compile time and no longer taking any time at time of execution. It still is something that happens at runtime. So that's why declaration is a fully featured programming statement. It's consuming CPU power and does something, just to be aware of it. Now, a few notes about the ideas about type safety in general, and we already said that strongly typed programming language strives to keep everything as safe as possible, and therefore what would be the set of ideals, like perfect environment to make it completely type safe? Every object will be used only according to its type. Nothing wrong with that. It's an okay rule to follow. This is why we're giving all these different data types, so that we choose the most appropriate data type in every given case. A variable will be used only after it has been initialized. Compiler does not require us to initialize variables, but let's give this a try. Like let's try to compromise this rule. What if I go to my integer variable, and what if I remove the initializer? It's very likely that when the initializer is removed, it will have some kind of strange garbage value in it. Then, given this, without being initialized, does it make sense to start making computation with it? No, it's really, it's a tough bug to locate, and sometimes it's been maybe happening, sometimes it may be invisible, and it's just essentially this creates a situation of unpredictability. Who knows what's going to happen, right? So let's actually try building this, and our compiler here is so unhappy about it that it says error, uninitialized local variable count used, right? So it points here, it says, yes, I could give you this program, but look, it's just such a poor choice that you're making that I'm treating it as an error, right? I'm not gonna let you use this uninitialized variable. Like, if you really don't know what to initialize it with in this situation, okay, make it 0, right? Make it something, but provide, like, make your decision. Don't let it hang uninitialized. Bad idea. And direct violation of type safety, as we're trying to, keep it at all times. Only operations defined for the variable declared type will be applied. Again, to give you an example, an integer here, this count, right? If you look at it in memory, it is occupying 4 bytes on a 32-bit platform, 4 bytes. Each individual byte of these 4 could be used to store some character. Would this be an intentional use of an integer variable? Probably not. Okay, so that would be sort of like doing some strange things with an integer, which was not initially intended to. But you could do that, right? But this would be probably be not a good idea if you want to stay type safe. Every operation defined for a variable leaves the variable with a valid value. Another situation is that, for instance, you know that in math, division by 0 is undefined. It's possible to take a fractional point number and divide it by 0, and it will generate a special encoded value infinity. You probably don't want to write code which which could yield such a strange value out of your computation. You probably, very likely that you want to check your divisor whether it's 0 or not before you're dividing, because this computation is important to you. So anyway, there are ways to do things that leave things undefined, or simply with incorrect or unanticipated values. And that would be something that we need to be careful with, because this is totally programmer responsibility, right? Computer is pretty good at doing the computation, but at certain situations we can feed it the values which would do things in violation. So this was referring to type safety. Now, static type safety. Anytime a word static comes to the view, in a lot of things, it's something that is determined at compile time. Okay, so you can realize that errors could be happening as syntax errors at compile time, or errors could be happening on the runtime and causing program to crash. That would be much later than compile time, right? Program has to be compiled and linked before it executes. So static type safety ideas refer to things such as that program that violates type safety will not compile. Remember our attempts to converting double to an int. We could potentially force compiler to say, no, we're not going to allow it. And here the same thing was happening when I attempted to use uninitialized count. What happened? It actually yielded compile error, right? So that's an example of type safety, static type safety. Compiler reports every violation in an ideal system. So unfortunately, these two things right here would be very impractical if they were implemented in their entirety. Essentially, it would render a programming language which is very difficult to use, because some compromises simply allow programmer to make their own decision and say, I understand what I'm doing, I'm programming for a specific system or platform, or I know exactly what I'm doing, and I may be able to override these, ideals that may exist out there. So in practice, this is not 100% accurate. Dynamic type safety refers to things happening at runtime. Okay, so like for instance, division by 0. who knows whether our divisor will be a 0 or not. If it happens to be a 0, the CPU will not be able to divide by 0 and will stop program from execution. Right? In fact, if you have a value and you attempt to divide it by 0, when CPU gets this division instruction to execute, what it does, it looks at this instruction and it says, oh, the divisor is 0. You know what? So it stops the program execution immediately and reports to the operating system. This program is attempting to divide by 0, and the operating system, now it's up to the operating system what to do with this program. If you're not doing anything to handle that, it'll be just simply like give you some sort of error message saying attempt to divide by 0, and program will be thrown out of memory and the operating system will go back to its business, right? So that's the idea of the runtime error, and if you want to allow it to happen or not, it's a different story. So the book is giving a lot of this comparison between reality and ideals, and this is what makes the book very valuable, because it allows you to analyze different situations and gives you all sorts of examples. So back to the idea that type safety is a big deal. It's important. We want to write all of our code which is type safe and easy to maintain and easy to understand if something, if something happens inside of it that we were not anticipating, right? Type safety generally helps. So remember, type safety simply means that we have a good control of what we do. Integers are all in good shape. All the strings are in good shape, everything is initialized, formulas work flawlessly, results are correct. That's type safety. Basically, healthy environment is what type safety is, right? But at the same time, it's very hard not to violate it, because it's just like, if you try to do something non-trivial, you'll realize that this type safety gets in the way sometimes. And compiler sometimes can be frustrating because it gives you a lot of warnings and error messages, and sometimes you can create some workarounds, but in general, if it's trying to give you a warning, you probably should give it a significant attention. Not like, it still compiles and it still runs, but more to, to say, why is it giving me a warning? At least you have to understand what is happening and make your final decision based on your understanding, rather than ignoring warnings that allow you to still compile the program. So C++ is not completely statically type safe. It's possible to compile the code, which may result in a really badly behaving program. In fact, compiler will not give you any errors. Right? I'm just trying to sort of like go through these things, and of course, again, if you read the book, it will give you some examples. We have some examples later on there. And C++ is not entirely dynamically type safe, and it's just like this. I just mentioned this division by 0, right? You may have a situation where you know for sure that in your case division by 0 never happens. But if you use Java programming language, okay, if you use Java, in front of every division, Java compiler inserts a check for 0, okay, whether you like it or not. So therefore Java slows you down. So anything that needs to be guaranteed to be dynamically safe, because Java does not want your Java program to ruin the behavior of the entire Java virtual machine, in front of every division, it inserts a check, whether the divisor is 0 or not. And only if it is, then you can attempt it. In C++, it doesn't exist. If it's dividing by whatever is fine, but if it's a 0, yes, the program will crash. It's your choice. Right? So, but it's, safety versus efficiency and speed. But of course, we can write code with an ideals of type safety in mind, and that's the progress.